Hi, in this video I'll provide a detailed presentation of our CVPR2025 paper on enhancing privacy utility trade-offs to mitigate memorization in diffusion models. So from the title, there are two objectives in this work. First, we wish to address the issue of memorization in diffusion models, mainly focusing on improving the novelty and privacy of the generated outputs. However, at the same time, we often hear the term privacy utility trade-offs, which refers to the idea that protecting privacy often comes at the cost of utility. For instance, in text conditional diffusion models, safeguarding privacy may lead to outputs that are no longer aligned well with the text prompts provided by the users. This work aims to enhance privacy while keeping the utility loss to a minimum. Okay, so first, what is memorization in diffusion models? In short, it's a limitation of diffusion models. It refers to the fact that pre-trained diffusion models can actually memorize images from their training sets and later reproduce them during inference. This can be that the entire training images is replicated, which we refer to as global memorization, or only a part of the image is replicated, which we refer to as local memorization. Then you may wonder why we need to care about such issues. Why does it matter? Firstly, this raises concerns about the model's creativity and output diversity. Secondly, this raises privacy concerns and legitimate risks. Imagine that there are some copyrighted images in the training set, such as the faces of certain high-profile people or some artworks by living artists. Both model owners and users can be exposed to potential legal complications such as the violations of copyright laws. This isn't hypothetical. There have been real lawsuits filed against companies like Stability AI, Midjourney, and Runway AI. Artists have described Stable Diffusion as a 21st century college tool, remixing copyrighted works from the countless images used in its training data. Let's look at some examples. This slide shows instances of the first scenario, where the model memorizes the entire training image. In the first column, the real images are taken from the line dataset, which is part of Stable Diffusion's training set. Then in columns 2 to 4, we show 3 generations from Stable Diffusions. As you can see, they are identical to the training images, clear evidence of global memorization. Finally, in the last 3 columns, we show 3 generations produced using the same initial random noise, but after applying our mitigation strategy. There are 2 key observations here. First, our generations no longer replicate the training images, effectively reducing memorization and improving privacy. Second, the outputs are still of high quality. They are realistic and remain well aligned with the user prompt. This shows that the privacy has been improved with minimal sacrifice to utility. This slide shows instances of the second scenario, local memorization, where the model memorizes only parts of the training images. As seen in columns 2 to 4, the memorized regions don't necessarily span the entire image. The part being memorized could be any objects or even just the background. For example, in the first row, only the wall color is different from the training image. In the second row, it's just the patterns of the circular wall painting. And in the third row, it's only the copy design that differs. Once again, in the last 3 columns, we show generations produced from same initial noise, but after applying our mitigation strategy. And again, we observe that our method reduces memorization while preserving high quality and utility, demonstrating its effectiveness. How did we achieve this? Before diving into our methodology, let's first discuss the existing research gaps and analyze the privacy utility trade-offs in current mitigation strategies. Some existing mitigation strategies require retraining diffusion models on billions of text-image pairs or performing nearest neighbor search over these massive datasets during inference. So while they may be effective, they're simply not practical due to their inefficiency. More recent strategies have made great strides in efficiency. However, these often come with suboptimal privacy utility trade-offs. Either they fail to prevent memorization, raising privacy concerns, or they reduce memorization at a significant cost of utility, meaning that the generated images poorly align with the user's intent according to the user's prompt. Let's now look at some visual examples that highlight the research gaps in existing strategies. As we can see, Stable Diffusion often replicates training images. Using the same random seeds, the baseline mitigation strategy does manage to reduce some of these memorized generations. However, replications are still quite frequent, and when memorization is avoided, the outputs often suffers, producing visible artifacts and significantly reducing generation quality. In contrast, our method is able to reduce memorization while still preserving high utility, producing images that are both novel and faithful to the user's prompt. The previous examples focused on global memorization, so in this slide we present additional examples of local memorization, and once again, our method is able to reduce memorization effectively while still preserving high utility in the generated outputs. Okay, now that we've seen some qualitative examples of existing strategies struggling with suboptimal privacy-utility trade-offs, let's take a deeper look at the equations and analyze why this trade-off tends to be suboptimal. Here's the equation for the original classifier-free guidance, or CFG. It's a widely used technique that balances fidelity and diversity in diffusion model outputs. And the best part is, it can be applied directly during inference. CFG works by linearly guiding the unconditional noise prediction towards the text conditional prediction. Building on this, a popular and efficient one-step detection strategy proposed by Wen et al. And later improved in our iClear 2025 paper uses the magnitude of the differences between the text conditional and unconditional generations as a signal for memorization. Memorized generations consistently show larger magnitudes than non-memorized ones, making this a strong and effective detection signal. Now here's the baseline mitigation strategy that builds on this signal. The idea is to apply prompt engineering at the first inference step. It starts by computing mt-1, the magnitude at the first step. So if this value is below a predefined threshold lambda, the prompt is considered safe, and generation proceeds normally using the original prompt embedding EP, just like in Stable Diffusion. However, if the magnitude is above the threshold, then the prompt is considered at risk of memorization. In that case, the strategy optimizes the prompt embedding using the magnitude as a loss function, and continues updating until the magnitude falls below lambda. This new engineered embedding is then used in the CFG formulation in place of the original. Since this embedding results in lower magnitude, it's less likely to trigger memorization. Currently, the privacy utility trade-offs in mitigation strategies is governed entirely by one thing: the thresholding hyperparameter lambda. This figure illustrates the logic behind that. Essentially, lambda controls how many updates are made when optimizing the prompt embedding from EP to E star. Let's consider two extreme cases. If lambda is set very high, say infinity, then the magnitude will always be below lambda. That means we'll never detect any memorization cases, and the prompt engineering mitigation is never triggered. The number of updates is 0, so all generations are exactly the same as those from the original Stable Diffusion. On the other hand, if lambda is set very low, say 0, then every magnitude value will be above the threshold. That means every prompt is detected as having memorization risk, and we perform prompt engineering for all of them, even when it's unnecessary. This results in an extremely noised optimized embedding E star that drifts far away from the original user prompt. As a result, we get outputs that no longer align with the user intent, often with visual artifacts or irrelevant content. So formally, choosing a lower lambda improves privacy by reducing memorization risk, but at the expense of utility. Conversely, a higher lambda preserves utility but compromises privacy. It is also worth mentioning that other existing strategies follow a similar idea, modifying the prompt to preserve privacy, but use different methods. For example, some add random tokens to the prompt, while others inject Gaussian noise into the prompt embedding. These approaches can reduce memorization, but they sacrifice utility even more than prompt engineering. So in summary, existing strategies tie the trade-off entirely to the extent of prompt modification, but prompt modification, especially when excessive, leads to a major drop in utility. In this work, we rethink the problem and ask ourselves, is prompt optimization really the best way forward? Are we sacrificing too much utility just to reduce memorization? And more importantly, can we design a mitigation strategy that doesn't heavily rely on modifying the prompt, yet they can still achieve a better privacy-utility trade-off? To better illustrate our improvements, let's begin with a simple geometrical analysis of the baseline method. There are two key components in classifier-free guidance, or CFG. The first is text conditional prediction, and the second is the unconditional prediction. In the baseline's prompt engineering strategy, we modify the text conditional term from EP to an optimized version E star, as shown here in blue. This figure visualizes the privacy utility trade-off. Point O represents a training image, so the inner contour shows outputs closer to O. This indicates lower privacy. The outer contours represents outputs that are more different from the training image, hence higher privacy. In the CFG framework, generation starts from point A, which is the unconditional prediction. The guidance moves the output towards the text conditional direction. In the worst case, using the original prompt EP leads to the point O, a memorized generation. To avoid this, the baseline method applies prompt engineering. It updates EP to E star, moving the generation from point B to C to D as more updates are made, progressively shifting it away from O. The process stops when we reach the desired privacy level. Fewer updates preserve utility but don't reduce the memorization enough. More updates improve privacy but at the cost of utility. From this visualization, we started to question whether we could rethink the roles of these two components in the CFG framework. Again, the text conditional prediction and the unconditional prediction. We observed that the suboptimal privacy utility trade-offs in existing methods actually stem from the two key components used in the current CFG framework, despite this being standard across diffusion models. First, we find that the text conditional term in CFG, when optimized purely for privacy using prompt engineering, can significantly reduce text alignment. This shows the need for alternative approaches that can preserve privacy without sacrificing alignment with the user's intent. Second, we notice that the unconditional term in CFG is not particularly effective as an anchor for guiding generations away from memorization. This suggests we should explore better anchoring points, ones that can more effectively promote privacy. So in this paper, we propose two carefully designed strategies, each aimed at refining one of the two CFG terms. Together, they lead to significantly better privacy utility trade-offs in diffusion model generations. Let's look at our first strategy, prompt re-anchoring or PR. In the standard CFG setup, there are two key terms. In our first strategy, the text conditional terms remain unchanged. We still use the engineered prompt E star in replace of the original user prompt EP to help reduce memorization. However, we argue that EP is being discarded too harshly. Think about it. Memorization is detected only when the model is conditioned on EP. That means EP is actually a useful negative example. It's a signal of what we don't want the generation to replicate. So instead of throwing it away, we propose using EP as an anchor point, replacing the second term in CFG, which is usually the unconditional prediction. Visually, this means that rather than guiding the generation away from the point A, the unconditional prediction, we now guide it away from point O, which is the memorized generation triggered by EP. This grainer row represents the new direction of guidance. It pushes the generation out of the low privacy region more effectively than the baseline CFG, which uses a less informative anchor. Although prompt engineering applied during the initial sampling step can help reduce magnitudes in later steps, we observe that this effect isn't always stable. In some cases, the magnitude spikes back up later in denoising process, resulting in memorized generations. In this plot, the blue line represents a generation from Stable Diffusion without mitigation. As you can see, it maintains high magnitude throughout the process and ends up producing a memorized output. Both the orange and green lines apply prompt engineering at the first step. However, the orange line does not apply our prompt re-anchoring strategy. As a result, although the magnitude is initially reduced, it quickly spikes again after around 10 steps. This shows that the low magnitude condition isn't preserved throughout inference, and the generation eventually reverts to a memorized pattern, similar to Stable Diffusion. In contrast, the green line uses our proposed PR strategy. So PR continuously diverts the generation away from the initially identified memorized condition throughout the entire inference trajectory. The effectiveness is evidenced both qualitatively from the final image appearance and quantitatively from the similarity score shown in the figure. Let's now look at our second strategy, semantic search or SS. In this approach, we build upon our previous improvements from PR, so we retain the anchor term as the original user prompt EP. However, as we mentioned earlier, prompt engineering, although helpful in reducing magnitude, often causes the prompt to lose semantic alignment with the user's original intent. So instead of modifying the prompt embedding directly, we propose using semantic search to find an alternative prompt that achieves a lower magnitude, while preserving the original intent as much as possible. Implementationally, we use a large language model to find up to 25 semantically similar alternative prompts. The search stops early as soon as one of these prompts results in a magnitude lower than the predefined threshold, lambda. If none of the 25 alternatives fall below lambda, we simply choose the one with the lowest magnitude. In geometric terms, this is like reaching the target privacy contour, points B', C', or D'. Now, even if point B and B' lies on the same privacy level, the utility of B' is typically higher, showing that the semantic search allows us to maintain utility while achieving the same privacy. This figure demonstrates the superiority of semantic search or SS strategy over the baseline using a widely studied memorized prompts. So the prompt name is the No Limits Businesswoman Podcast. In the baseline's prompt engineering strategy, the magnitude is reduced to 1.15, successfully avoiding memorization. However, this comes at a significant cost to semantic alignment. The modified prompts drift away from the original meaning, as shown by the low clipped similarity scores, for both the engineered text prompt and the final generated image. In contrast, our SS strategy reduces the magnitude even further, down to 0.78, and still effectively prevents memorization. But more importantly, it preserves the user's intent. By exploring the linguistic space, it discovers the alternative prompt, the Empowered Businesswoman's Podcast, which is a version that is both privacy-preserving and semantically aligned. Putting it all together, this figure compares our proposed strategies, PR and SS, against the baseline. Before we wrap up, I'd like to highlight an important synergistic benefit between our two strategies, PR and SS. While SS is excellent at preserving the semantics of the user prompt, it can sometimes fail to find an alternative prompt among its 25 candidates. So it cannot achieve a sufficiently low magnitude to fully protect privacy. In the example shown here, even though SS doesn't find a low enough alternative, it still reduces the magnitude from 7.48 to 6.02. And that's just enough for PR to step in. By using the original prompt as a new anchor point, PR effectively steers the generation away from memorized content, achieving strong mitigation despite SS falling slightly short on its own. This example highlights how these two strategies complement each other, making the overall approach more robust and effective. Now let's look at some results comparisons. Remember, the mitigation strategy is only triggered when the detection strategy flags a generation as a memorization risk. So here, we test two baseline detection signals, M and M', and compare performance using our PRSS approach versus the standard prompt engineering. That gives us 4 lines in each figure. We evaluate both global and local memorization scenarios. On the horizontal axis, we measure utility using the text alignment CLEAP score, so larger is better. On the vertical axis, we measure privacy using the average SSCD similarity, so smaller is better. This means that the curves lying further to the bottom right indicate better privacy utility trade-offs. As the figure shows, PRSS represented by the red and green lines consistently outperform prompt engineering, which is the yellow and blue lines, across both detection signals and for both global and local memorization. Notably, in the global memorization case, PRSS delivers large improvements over PE. For example, moving from the blue line to the green line, or from the yellow line to the red line, shows how much more effective PRSS is. For local memorization, the margin of improvements is smaller but still significant. Even when using inferior detection signal M, PRSS, which is the green line, performs on par with the baseline method that uses M prime. For local memorization, the margin of improvement is smaller but still significant. Even when using the inferior detection signal M, PRSS, which is the green line, performs on par with the baseline method that uses the superior detection signal M prime, which is the yellow line. And when equipped with the M prime, PRSS, which is the red line, achieves state-of-the-art performance, demonstrating its ability to fully capitalize on stronger detection signals. Now, some existing strategies also use alternative privacy matrices, such as the localized similarity scores, the 95th percentile of SSCD similarity, or even the percentage of generations classified as memorized using a 0.5 threshold. We've tested PRSS using all of this, and the results are consistent. Our approach always lands in the bottom right corner, showing the best overall privacy utility trade-off across the board. For the ablation studies, this figure highlights the necessity of including both components in our PRSS method. As shown here, the red line, which represents the full PRSS strategy, consistently lies further to the bottom right compared to the yellow and green lines, in both global and local memorization scenarios. The yellow line shows performance without semantic search, while the green line shows performance without PR. The synergistic effect of combining PR and SS, as we earlier mentioned, is particularly evident in the local memorization scenario. This aligns with our observation in our recent iClear 2025 paper that local memorization poses greater challenges for existing mitigation strategies. Using PR alone can boost privacy, but it does so at the expense of utility. On the other hand, SS alone improves utility, but its privacy gains are limited. Together, they complement each other, leveraging their individual strengths to achieve the best privacy utility trade-off. In the global memorization case, each component, PR or SS, already outperforms the baseline on its own, but when combined, they further enhances the trade-off, demonstrating the robustness of PRSS across both global and local memorization challenges. Here are some qualitative results demonstrating that our proposed PRSS is able to reduce memorization while still preserving high utility, producing images that are both novel and faithful to the user's prompt. In contrast, existing baselines often suffer from poor text alignment or fail to effectively prevent memorization. These are some examples of global memorization scenarios. And these are examples of local memorization scenarios. To wrap up, we introduce PRSS, which consists of 2 carefully designed strategies, prompt re-anchoring and semantic search, each aimed at refining one of the 2 key terms in the classifier-free guidance framework. Together, these 2 components lead to significantly better privacy utility trade-offs in diffusion model generation, effectively addressing memorization while preserving alignment and output quality. It is also worth mentioning that PRSS is highly efficient in practice. All we need to do is adjust the two terms in the CFG equation with no need for retraining, fine-tuning, or searching through the training set. Finally, regarding limitation and future work, PRSS relies on the accuracy of a predefined detection strategy to trigger the mitigation mechanism. So one clear direction for future research is to develop more accurate and robust detection methods. Improvements in detection would orthogonally strengthen PRSS, making it even more effective in mitigating memorization. Thank you for your attention. Please check out our paper and project page for more details.